Okay, so I think this will be the final one, but we'll see how we get on in the live lessons. So, exoplanets, how do we know they exist? Well, are they? To start with, I guess, well, an exoplanet is a planet outside of our solar system. So we know of the 8 plus Pluto, and then plus all the other small dwarf planets within our solar system. And what we want to know is how many of them are there outside of our solar system? And do other stars have planetary systems? Now, that was a key question for astrophysicists in the 80s and 90s. Do other stars have planetary systems? Now, of course, our likely answer is yes. Our star's got planets. Why shouldn't all the other stars have planets? We don't know for certain that's true. And even if the other stars do have planetary systems, do they look like ours? Is ours typical, or is there something unusual about ours? And so this is a good scientific question that we would like to answer for. A couple of methods suggest themselves, and this one is the one that sort of had the best chance in the early days of actually producing a result, which is to use the same Doppler shift method that we use for binary stars to detect larger planets. Because, of course, the star and the planet actually go around a common centre of mass, which isn't dead in the centre of the star. And so as the planet goes that way, the star goes that way. And so if we can measure the spectral lines from the star with enough accuracy, we can measure a small Doppler shift in the motion of the star because of the planet going around it. Now, of course, it's only really likely to work with larger planets because they've got to be heavy enough to make the star move. And I've whipped some details for that off Wikipedia. It says the speed of the star around the star system centre of mass is much smaller for that of a planet because the radius of its orbit is so small. The Sun moves about 13 meters per second due to Jupiter, but only 9 centimeters a second due to the Earth. But with modern spectrometers, we can measure down to 3 meters per second. So we ought to be able to find another star, and if it's got a Jupiter-like planet, measure the Doppler shift due to that Jupiter-like star. And in truth, that's getting quite close to the limit of what these things can do. So we're probably looking to find bigger stars than Jupiter, or bigger planets than Jupiter. Sorry, not stars, bigger planets than Jupiter, or planets that are orbiting more closely into their star, so they move their star a bit more and move their star a bit faster because the planet itself is going around quickly. You got to remember, Jupiter takes long to do its orbit because it's quite a long way out. Anyway, this method is called the radial velocity method, and you have to remember that because they describe it that way in your exam. And here's a plot of a radial velocity method measurement of a planet, and the planet is 18 Del, and it's planet B, so our planet A has already been discovered, and you can see the shift in the frequency of the spectral line within the star that's been converted into a radial velocity, and you can see that the star has an orbital period of around about 3 years. The planet has an orbital period of around about 3 years. I'm going to do this all the way through this thing, and I'm going to say star when I mean planet. The planet has an orbital period around the star, making the star wobble by up to 100 meters per second of 3 years. So a big old planet with respect to its star, to be able to make it be moving by 100 meters per second, but also relatively close in, orbit of 3 years, puts it sort of orbit of Mars. It's certainly not out at Jupiter, so relatively close in. So this is the radial velocity method, as you saw on the previous slide, 1995. First time that convincing radial velocity method measurement of an exoplanet is done. Since then, a lot of planets have been found using the radial velocity method. Okay, so there they all are, and you can see that the vast majority of them are heavy old planets, whereas it's only in recent times have the spectrometers become good enough to be able to find this kind of change in the velocity of the star due to an Earth-sized planet orbiting around that star. It's more likely to be Jupiter-sized planets or bigger. this is 10 times Jupiter up here, that are orbiting the star, making the star wobble, and then us using that wobble to detect its radial velocity and work out what's going on with the planet. Now the other method is the transit method, and here I've illustrated it. This is an exoplanet. This is Venus and the Sun as seen from Earth, and this gives you a clue as to the problem. The size of Venus compared to the size of the Sun is very small. So the dip in the amount of light for a planet about the size of the Earth, Venus is about the size of the Earth, is going to be very small. Now, of course, we're observing this star from huge distance away, so we're not seeing this as per this picture. What we're seeing is an unresolved star, so we can't tell one side of the star from the other side of the star. The star is a pinprick on our CCD. We've got an unresolved star whose light goes down a tiny amount when a planet transits in front of it, and transit means pass between us and the star. Usually, when it was the term was first invented, of course, it was talking about Venus and Mercury passing between us and the Sun. So this is a picture of the transit of Venus. Venus does 2 transits in a row and then no transits for a very long time. So over the last 10 years, it's done 2 transits in a row, and then it's not due to do any transits for a long period. So how did astrophysicists decide that they were going to have a look for the transits of stars? They needed a lot of data. They needed to be staring at a star for a long time to be able to see its light dip, and they needed pretty reliable data, pretty smooth data. So they didn't want the atmosphere to be mucking things up, and they needed to be staring at it for a long period, so they didn't really want the fact that the atmosphere lights up when the sun comes up to be mucking it up. And so it was decided to launch a robotic space platform that was called Kepler. We will do when we do fields that Kepler was the chap who worked out what was going on with the orbits within our own solar system. And the Kepler Space Telescope was launched and positioned so that it could always stare at this patch of space with this array of CCDs. And you can see that there are 42 CCDs, and each one is a couple of million pixels. And so the thing has over 90 megapixels, which at the time when Kepler was launched was absolutely huge. 2009, I think Kepler was launched. At the time Kepler was launched, absolutely huge. Today, my digital camera's got 22 megapixels. So in order to get up to 94 megapixels, you'd only need 4 or 5 of my digital camera's CCDs. You wouldn't need 42 CCDs. But that just shows how fast this technology has changed in the intervening years. But at the time, this 96 megapixels was massive. Kepler was then designed to stare at this space. And of course, the way it's designed to stare at it is that we have a curved mirror, and then we have the array of CCDs here. So our light comes in, bounces off our curved mirror, and focuses on our array of CCDs. And then within the field of view of our array of CCDs, we have thousands of stars. The Kepler Space Science team designated which stars they thought were good candidates for possibly hosting planets. They spent the first little while working out which of these stars they'd picked were actually variable stars and therefore no use whatsoever for the survey. And having eliminated the variable stars, Kepler stares at the rest of them, recording their light intensity to see if at any point any of them go down, and preferably go down and come back up again at regular intervals, because then that would be an orbiting planet repeatedly transiting in front of its star. Now, just as an aside, we've got to mention CCDs. They're on the course. I've got to talk about them, and I've not talked about them up till now, although I've mentioned the term a lot. It stands for child coupled devices, And when digital imaging was first invented, digital imaging always used CCDs. And so the term that we use to refer to the light collecting detectors for a camera or a telescope is CCD, although today actually the vast majority of them don't use CCD technology. They use something slightly more advanced, I think, called CMOS. The idea behind the CCD technology is that incoming photon strikes an electron. They're marked on here in blue, aren't they? Excites the blue electron, and the blue electron then jumps up out of the valence band and into the conduction band. Having been allowed to be free to move, our electron is then collected underneath this gate. That's this bit of, and that because that gate has a positive voltage on it. So light hits our pixel. This is pixel. Light hits our pixel. It frees an electron. Electron jumps up the conduction band, can move about. It moves to underneath that metal plate, because that metal plate has a voltage on it. And all the time while the picture is being exposed, all the electrons which are disturbed by the incoming photons collect under that metal plate, and so that we can count them. Now, the clever bit about the CCD is the bit that's going on in the animation here, is that at the time when CCDs were invented, electronics were not good enough to be able to connect up each gate and measure the voltage and measure the number of electrons at each gate. And so what happened was that once the electrons had been collected at the gate, they were moved sideways. Across to the next gate, there you go, moved across to the next gate. And then moved again, across to the next gate. There you go, across to the next gate. And then eventually, they pop out the end of the CCD. And when they pop out the end of the CCD, they get counted. So instead of having to put an electron detector here and here and here, we only have one electron detector at the end, and we measure each set of collection of electrons that are collected under each pixel as they pop out the end. Which is what's called a charge coupled device, because the devices are coupled together. The charge is moved from one to the end, and it's all shuffled out. Shuffle it out, measure it, shuffle it out, measure it, shuffle it out, measure it, until you've shuffled out the entire row worth of CCDs, the entire 1,000 worth of pixels out the end, and measured how many electrons have collected under each gate for each electron. So that's a charge coupled device. It's not what happens now. It's now CMOS. But we call them CCDs still. Now, you might spot a problem if you're paying close attention. The light, I'm going to rub out all of this scribbling. Sorry. The light comes from up here. That means that this metal contact, and that metal contact, and that metal contact, and these wires are all in the way for the incoming light. That makes our CCD inefficient, because quite a lot of the light just bounces back off that gold contact and doesn't actually enter the bit of silicon so that it can make the electron jump up into the conduction band and move about. So our charge coupled device is inefficient because the metal of all the gates and all the wires gets in the way of the incoming photons. Seems bizarre, doesn't it, that you would design things that way? But oddly, the eye is designed that way. All of the neuron detectors and all of the connections between the neurons and all of the blood vessels that carry the energy to your light detectors, your rods and your cones, all of that is on top of the rods and the cones. It gets in the way, reducing the efficiency of our eye. Obviously, the very first sort of very primitive light detectors that were first created in the ocean, in some ocean animal, and proved to be useful to that ocean animal, and therefore got passed on to all of its successors, was that way up. And it hasn't changed since. So actually, our eyes are very inefficient. And early CCDs and early CMOS were very inefficient. And the problem is that this layer of silicon is roughly 0.5 millimeter thick. Silicon wafer comes between 1 millimeter and 0.5 millimeter thick when you buy it. It's still amazing stuff, but it's still but that's too thick for the light to penetrate. So the light can't come in this side and have an effect up here. And so our CCDs were limited. Well, what they do today is they thin this down. This is reduced from about 0.5 mil down to maybe 0.1 of a mil. And at that point, the light can enter from this side. And then the wires and things don't get in the way. And so that's been a massive improvement in the CCDs recently. And there you go, they're called back thin CCDs. And you can see that the back thin CCDs are hugely better, much more efficient than a standard CCD. Because the light is no longer being blocked out by all those wires and all those gates. It's coming in the other side. And so back thin CCDs were invented for telescopes so that we weren't losing any photons. You know, you build a giant telescope and then you reject half your photons because they're bouncing off the old wires. So back thin CCDs were invented for telescopes. They have now entered normal cameras. They've entered sort of SLR cameras over the last 5 or 10 years. And are now going into phone cameras. This is why the top-end phone camera suddenly is massively better in low light than they ever used to be. All the TV adverts advertising how good the cameras on the phones are in low light. That's because the top-end phone cameras now are back thin CCD. The light is coming in from this side. It's not coming in from this side, even on phone cameras. So technology that was invented for telescopes has now made it into phones. And this thing, quantum efficiency, you have to know for your course. So quantum efficiency is the number of electrons counted by our detector compared to the number of incoming photons. So the aim is 1 photon gives 1 electron. And that electron gets counted. That's the aim. And you can see here, back thin CCDs are not very far away from that aim. By comparison, we're right down here under 10%. 2 sorts of light. Scotopic is your rods, and photopic are your cones. Scotopic are much better in low light conditions because they have a higher quantum efficiency. When you're in low light conditions, your cones turn off, which is why you think all stars are white, and that's because your cones, your colour discrimination has turned off in the low light conditions, and you have to stand out there and wait for a long time, wait for your eyes to open right the way up, so that your cones start to detect colour again, and then you can see that stars did have some colour. But initially you can't, you're relying on your rods. These numbers are required for your course. Modern CCDs, back thin CCDs, have quantum efficiencies greater than 80%, whereas the eye, on the other hand, is under 8%. And they're linear. 1 photon, 1 electron. Whereas the eye is anything but linear. We've discussed the fact that there's this crazy Hipparchus log 2.51 scale. Because the eye is not linear. The eye is not 1 photon, 1 activation, and your brain going, oh, there you go, one photon. Is anything but linear. So your eye is logarithmic, and your CCDs are nice and linear, and nowadays really close to 1 photon producing 1 counting electron. Okay, that is required from the course. Bit of a sidestep from exoplanets, but is required for your course. Anyway, getting back to Kepler. So Kepler stares at these stars and starts detecting their light levels. And here you go, satellite levels from a star. And Kepler very successfully starts to find regular, repeating dips in the light of some of the stars. But look how much it's going down. 0.6%. I mean, this is pretty good stuff, that it can stare at these stars and measure dips of 0.6% for a star. You know how many how many tens of parsecs away, and we're detecting 0.6% and a drop of its brightness. And because it's happening with regularity, we know we've got a star. We know we've got a star with a planet. Sorry. Now, this planet is what's called a hot Jupiter. i.e. it's a Jupiter-sized planet, but it's really close into its star. And before Kepler went up there and started looking, We had no idea that the galaxy was full of hot Jupiters, but the galaxy is full of hot Jupiters. And that has been a fundamental challenge to our understanding of the way that the solar system was born, because we have cold Jupiters. Our Jupiter is a very long way away from the sun. It is not close into the sun, orbiting in days. It's out some way from the sun, orbiting in years. And our image of how the solar system was formed was that the rocky stuff formed close in where it was hot and where the rocks could condense, and then the gassy stuff forms further out where it's cool and the gas can condense. Well, if that's true, what the hell are all these hot Jupiters doing turning up in our Kepler survey and in the radial velocity surveys as well? What are all these hot Jupiters? And now the thinking is that actually solar systems are born with their gas giants close in, and then what happens is they all reshuffle, which seems absolutely extraordinary. But that's the explanation scientists have had to come up with, because they're finding these hot gas giants close into the stars with large regularity. Now, of course, you might be saying to yourself, but of course they're finding hot Jupiters with regularity because they're the easiest to find. So therefore, it looks like there's loads of hot Jupiters out there when there's not that many hot Jupiters out there. It's just that they're easiest to find. And of course, that's true. There is an element of that about what's going on. Now, the transit information from Kepler doesn't just tell you that there is a planet there. If you have a look at this, of course, it's telling you about quite a lot about what's going on. This dip here between the dotted lines on my second diagram, how long that takes, tells us about the size of the planet compared to the star, as does the depth here. But also notice this curve to the base. The reason there's a curve to the base is that due to the curvature of the planet, of the star itself, the outer edges aren't sending quite as much light in our direction as the center is. And so when the planet is going across the outer edges, it's not blocking out quite as much light as it does when it goes across the center, and so we get this curve to the bottom. And the combination of these things actually allows us to be able to tell whether the planet is going dead across the middle of our star or whether it's only grazing an edge. And so this kind of information, by going into real detail of the shape of these things, is allowing planetary scientists to work out a great deal about the exoplanets they're finding. It's not just that there's an exoplanet. They're actually beginning to find sizes. From the orbits, you can work out masses. You can find out whether it's going across the middle, where we're actually looking at it side on, or whether it's going in at an edge. Lots and lots of stuff can be worked out from this. There's also other things on the other transition. If the other transition starts off slightly higher and goes down deeper, that means the planet itself is radiating light, and we lose that little bit of light when the planet disappears behind the star. So we might get a little tiny transition on the other side, because the face of the planet that faces the star and therefore is facing us when the planet's on the other side is incredibly hot, because the thing is close in. So you can start to get ideas about the temperatures of your planet. All sorts of information can be obtained, providing we get this kind of level of detail and level of stability. Look how stable this star's relative output is. Now, unfortunately, Kepler broke down. So Kepler only operated in its main role for 4 years. And then one of the reaction wheels broke. And then the second reaction wheel broke. And once 2 reaction wheels were broken, it couldn't carry on pointing in the same place anymore. They've carried on operating it because it points generally in the right place, and so you can carry on tracking stars, but it doesn't operate as well as it once did. But in that 4 years, it collected enough data to confirm 2,300 planets, with another getting on for 4,000 unconfirmed and plenty of binary stars as well. Wow. Kepler is just most amazing space mission ever. And Kepler went up, we knew a handful of exoplanets. After Kepler's done, we know thousands of exoplanets. Exoplanet, the answer to the original question, do stars have planetary systems, is a very conclusive yes, stars have planetary systems. So this lot in blue up here, they're the radial method. You can see heavy and relatively far out from their star. This is AU, so 1 AU is being at the same distance from the star as the Earth is. And then all of these, this mass in red here, this is Kepler's detections. And you can see they're all close in, because Kepler only operated for 4 years. Now, if you want repeats, if you want repeating dips so you can confirm you've got a planet, you're only going to get repeating dips if it only operates for 4 years. If the planet is going around its star more often than a year. They have to be closer in than a year. They have to be closer in than 1 AU in order to give an orbital time which is less than a year, so that we get plenty of repeating dips to confirm that they are a planet. And so you can see these good mass of planets that Kepler has found, all running from sort of a tenth of a Jupiter downwards. And then we've got this second set up here, also found by Kepler, and these are our hot Jupiters. You can see only a tenth of the distance between them and their star that there is between us and our star, and yet their Jupiter mass is going up to 10 times Jupiter's mass. So these are our hot Jupiters, and then these are all of the rest of the planets that Kepler has found. And then these planets are the ones that the radial velocity is more sensitive to. Kepler sensitive to planets under 1 AU, the radial velocity more sensitive to heavy planets. So it's finding the heavy ones, the Jupiters and heavier, not so sensitive to smaller planets. And then there are a couple of other methods, so you can see some other colours on here. There are a couple of other methods. They are microlensing and direct imaging. And so they come sort of further out. In fact, I've taken the direct imaging off because the direct imagings are out above 10 AU, and it made this graph, compressed up this graph too much. So I've taken the direct imaging ones off. So these green ones I think are microlensing, but they're microlensing and direct imaging, not particularly. So this is the summary of where we stand at the point this graphic was put together, and you can see that the vast majority of planets fall between the Earth and Neptune. And that turns out not just to be a bias in the system. So the system is biased towards close-in planets and larger planets. Bigger dip in the light, more important the transit, more likely to be detected. Close in, more likely to have regular repeats, and therefore more likely to be detected. But even when you make allowances for the biases that there are within the transit method and the biases that there are within the radial velocity method, even when you make allowance for that, you find that the most common size of planet in the universe, in the galaxy, sorry, is between super Earth and small Neptune. So it lies in that gap. And they're called super Earths if their density, if you can get an estimate of their density, if their density is sort of iron-like density like the Earth, or if their density is gas-like, then it's a Neptune. But that size bracket is where we find most planets. And of course, the little ones, very, very hard to detect with the transit method. And so the transit method biases against these. But when you consider the bias and you actually multiply up, then you realise that actually there's a hell of a lot of little planets out there. Little planets are not uncommon. There are loads and loads of them, because if we can detect 5 of them with a system that just is never going to detect them, then there must be huge quantities of them. So lots of little planets and lots of super Earths. That's the conclusion from the work of Kepler. Now this is a paper that I was having a look for some papers that had worked on working out, what the population of planets was in the galaxy, allowing for the biases that the Kepler detection system or the other detection systems had. And you can see here that that's what the blue line is. So the blue line is their calculated probability density function The blue line is their calculated probability of finding planets with around stars, and you can see that probability shoots up when we get to a orbital period of about 10 days. So planets that are going around their star in just 10 days are very common, and then our probabilities of finding planets after that just goes up from there. But 10 days is our edge, really common around 10 days. And you can see by comparison, Mercury, Venus, Earth and Mars are, slapping pretty probable. Then this is the probable radii of stars, of planets. And I said that planets, little planets, are really quite common. And you can see that we don't have that many Jovians, we don't have that many Saturns. Then they shoot up when we get to Neptune's size and carry on going up from there, a probability density function. And so, again, the terrestrial planets all fall into a pretty common size of planet to find. Neptune and Uranus just fall on that edge where the super Earths and the Neptunes form, whereas the big gas giants, not quite so many of the big gas giants. And then where are we? Period ratio. Yeah, so this is the ratio between pairs of exoplanets where they've got multiplanetary systems and the pairs within the Earth. And you can see that the ratio, the sort of the spread of between one planet to the next planet to the next planet, our terrestrial planets on the solar system fall pretty much in the middle of the probability density function, and they're pretty likely. The place that's unlikely, the bit that's seriously unlikely, is this bit. I said to you that for the inner planet, it's likely to be at a period of 10 days. So there's the peak for the inner planet being at a period of 10 days. Mercury and Venus, long way outside 10 days, more like 100 days. Where our solar system is unusual is that we don't have any of these close-in planets. So this was the conclusion of Mulders et al. In a paper from a couple of years ago. This is their quote. Overall, the solar system seems to be pretty typical in terms of planetary radius, planetary period ratios, inclination, and planets per system. The only clear difference is in the period of the innermost planet, where the solar system is an outlier. While also the lack of super Earths and mini Neptunes in the solar system is also notable. Earth-sized planets are not intrinsically rare, and the size of the terrestrial planet does not make the solar system an outlier. So it's not that the size of the planets that we've got are rare, it's that we're lacking the really common sized planet, which is our super Earth or mini Neptune. So solar system is unusual, not massively unusual compared to our projection of what planetary systems there are around all the other stars, but it is unusual. Now, of course, part of the reason for wanting to do this is we want to know, is there life out there? And of course, you can make a calculation for how far away you have to be from your star in order to have a reasonable chance of there being liquid water. And then if there's liquid water, then there's a good chance of life occurring. And so that's called the habitable zone, or the Goldilocks zone, as in just right, if you know the story of Goldilocks and Three Bears. And of course, the position of the habitable zone changes with the brightness of your star. If your star is a pretty crummy thing, then your habitable zone is quite close into the star. Whereas if your star is big and bright, then your habitable zone is a long way from it, simply because your star's that bit hotter, so you've got to be that bit further away in order to have liquid water, not to have had the water boiled off the surface. Okay, so that's the habitable zone. And so one of the questions that astrophysicists have been asking since Kepler has been producing all these huge number of planets is how many planets are we finding within the habitable zone? What chances are there of finding life out there? Are we finding sort of reasonable sized terrestrial planets in the habitable zone where there's a good chance of life, or are we not? So that question turns up a lot for astrophysicists. And this is a review paper. I've taken some quotes from this review paper by Natalie Batala. She has been one of the chief scientists involved with Kepler from the very beginning. She's now a professor at one of the California universities, and she was named in 2017 as one of the 100 most influential people in the world by Time magazine because of her work with Kepler. So quite an important woman. And I found a review paper by her that talked about this stuff and talked about the habitable zone. She refers to it as HZ in her paper. So this is just straight out of her paper. And she finds that planets orbiting in the HZ zone are less common for G and K stars than they are for M-type stars. Now, of course, Oh Be a Fine Girl, Kiss Me. Girl, G, that's the Earth. It's a G-type star. The Sun, right? Sorry, there is a G-type star. K are the ones next door, going slightly cooler, and then M is quite a lot cooler. So what we're finding is we're getting plenty of planets within the habitable zone of smaller, cooler stars. We're not getting quite so many planets within the habitable zone of stars like our own Sun. Now, again, there could be some biases to that. I'm sure that a scientist as eminent as Professor Batala will have thought about this, but there is going to be some bias in there in that M-type stars are little dinky stars. And it's much easier to find a planet around a little dinky star because the planet is going to have a bigger impact on the light from the star. It's also much easier to find planets around little dinky stars by the radial velocity method because the planet's weight is going to be bigger compared to that of the star, and so the planet's going to move the star more. And also, finally, of course, the habitable zone for little dinky stars is much closer in, and that's exactly where Kepler is finding all of its planets. Kepler's bias is towards planets that are close in. And so Kepler isn't really going to be finding anything in the habitable zones of F-type stars, brighter than the Sun, because those planets are further out, will be further out than the Earth is. And Kepler wasn't really finding planets that were further out than the Earth is. It was only finding ones that were closer in. And so Kepler is likely to find planets in the habitable zone of cooler, smaller stars. And so this is perhaps no surprise, but I say I'm sure the professor has given that some thought when she wrote this. However, interesting, I thought more interesting was collectively the statistics emerging from the Kepler data suggest that every late-type main sequence star has at least one planet. 1 in 6 has an Earth-sized planet. And that small HZ habitable zone planets around the M dwarfs, the red dwarf stars, are really common. They abound. And that Kepler's already found evidence of potentially habitable planets within 5 parsecs of us. So what's that, 20 light years? No, 15 light years. Okay, so and this was written as a reasonably readable review paper. It wasn't written to be very, very technical, so I was lucky to be able to find this paper. And then I've just popped this one in because you might remember this. This made the news 3-4 years ago now. So you might remember all this happening. TRAPPIST 1, the star is called. And TRAPPIST 1, I've put RAPIST 1 there, look, TRAPPIST 1. Managed to cut the T off, sorry about that. TRAPPIST 1 is a really cool red dwarf, so right into the M's, piddling little thing. Its radius is only slightly bigger than Jupiter, but it's got 84 times Jupiter's mass because it's a whole lot denser because it is actually a proper star. And this thing has 7 terrestrial planets. You can see the 7 here: A, B, C, D, E, F, G, H. In the right sort of size for it to be Earth or Mars. You can see the comparison circles there. And 3 of those planets orbit within the habitable zone. So TRAPPIST 1 made a big splash when it first appeared in the news, that we'd found Earth-sized terrestrial planets around a star within that star's habitable zone, not too far away from the Earth. Of course, a very different star from our own, a very, very cool star. So if you were relying on taking your crops with you and growing your crops, you'd struggle, because photosynthesis requires red light and blue light. And of course, a cool red dwarf is not going to be producing a whole lot of blue light. So your green plants probably not going to do very well, but still exciting. And you can see the transits data. This isn't from Kepler, this is from Spitzer. Spitzer being a proper space telescope with a big old brain stopped with a big old mirror. And Spitzer was specifically designed to look in the infrared, and so Spitzer's a good choice for having a look at a really cool star. And so Spitzer was directed to have a look at TRAPPIST, and this is its data for the various transits of the various TRAPPISTs. Okay, not on our course, just interesting. Now, future. Can you see that this GIF in the corner here is running? We do have the capability with the current best telescopes that we have of imaging exoplanets. So this is a set of, is it 4 or 5 Jupiter-sized planets going round a star, going on round so they're flat onto us. So this couldn't have been detected with the radial velocity method or the transit method, because it's flat onto us. But because it's flat onto us, we've got an opportunity of taking photos of it. And what's been done is that the star itself has been blocked out. So this center odd thing going on here, that's that central star. The light from the central star has been blocked out, so that you've got a chance of being able to see the planets. And then you can probably see the diffraction pattern that's then forming, the sort of airy disk or inverse airy disk that's going on there, because of the blocking out of the light from that central star. And then having made all that mess by blocking out the light from the central star, you've then got to be able to pick the planets out from that. And these planets are glowing in the infrared, so this is a near infrared detection, so near infrared telescopes. And you might remember talking about atmospheric windows, some of the infrared does actually get through the atmosphere, particularly that quite close to visible, so the near infrared gets through. So if you look in the near infrared with your very best telescopes, you have a chance of seeing hot planets glowing, particularly if you can block out the light from the star. And so this is direct imaging of the rotation of multiple Jupiter-sized hot glowing planets revolving around their star, the star having been blocked out. And so we can direct image. It's interesting that the direct imaging hasn't found huge numbers of this, and so the conclusion is that long way out Jupiter-sized glowing in the infrared planets aren't actually all that common. But the plans are, I've called this the future, the plans are to build telescopes capable of resolving and imaging much smaller stars and much smaller planets. I've been saying stars all the way through this, haven't I? Much smaller planets and much closer into their host star planets than we can image at the moment. And of course, that level of resolution is going to require much larger telescopes. So this would be an example of this. This is the extra large telescope, which is the European Space Observatory is planning to build in Chile. That's got a huge mirror. So we're talking about mirrors, I can't remember exactly what the numbers were. I was quite shocked when I saw them. It might even have been as big as 100 meters across. I mean, just crazy sizes of mirrors. And the next generation of telescopes are designed to have these huge mirrors so that they've got a chance of being able to resolve, as it says here, planets down to Earth-like masses. And possibly to get direct images of their atmospheres and characterization of their atmospheres, because the best way to tell whether there's life on another planet is from looking at its atmosphere. The Earth's atmosphere is unique in having all this free oxygen and not having a whole lot of carbon dioxide because of the action of plants. So if we find other planetary atmospheres that have got a lot of oxygen and not that much carbon dioxide, we can be pretty sure that plants are doing very much the same thing on those planets. So next generation of telescopes, and I say the ESO are not the only ones, so the Americans are as well, designing these enormous engineering feats in order to be able to image planets in the future and get characterization of their atmospheres. How long have I been going? 3/4 of an hour. Not too awful. Okay, in summary, what do you need to know? You need to know there are two main exoplanet detection methods. The radial velocity method. It uses the Doppler shift of the star as the star orbits the system's common centre of mass, i.e. the star wobbles because the planet's going around it. Or there's the transit method, which uses the slight dimming of a star as an orbiting planet crosses between the star and us. That's the key thing that you've got to know. And then just sort of, if you're asked to discuss, both are more likely to find larger, close-in planets than they are little tiny things that are a long way out. Neither one, for example, would have any chance whatsoever of finding Pluto. Both are more likely to find planets around smaller stars because for the radial velocity method, the smaller star will wobble more with the action of the planet, and for the transit method, there'll be a bigger change in the brightness because the planet will be a size closer to that of the star. So both more likely to find planets around smaller stars, and they have indeed found lots of planets around M-sized stars, as we were discussing a minute ago. But the main conclusion from all the huge numbers of planets being found by Kepler is that most stars have planets. As I talked about before, the conclusion of one of the chief scientists on Kepler was that most late stage main sequence stars have got planets, if not planetary systems, and if it's an M star, it's almost certainly got terrestrial planets in its habitable zone. Okay, all that's interesting. This bit, absolutely required. Hopefully, that's the last time you have to listen to one of these.